Welcome back, ladies and gentlemen. So, we're going to be starting off with isotopes now. This is probably the main thing in this unit that you don't recognize from grade 10. Isotopes are, well, actually, you have been dealing with them for a while. You just didn't notice. Take a look at your periodic table, right? Pull yours out wherever you've got it. And if you look at it, or really any periodic table, what you're going to see is that there are, of course, the atomic numbers and the atomic masses. Let's take one as an example here. Lithium. Lithium's a good one. It says here on the periodic table that lithium has an atomic number of 3 and an atomic mass of 6.94. 6.94. That's a weird one, isn't it? Like, if I draw a Bohr diagram of lithium, lithium has 3 electrons, so 2 electrons in the first shell, and 1 electron on the outer shell. And in the middle, it's going to have 3 protons and, well, how many neutrons? You guys learned the rules on how to do this a while ago. You would take 7 and you would subtract 3, right? So 4. And there's lithium. And that's what you've used ever since you first learned about this stuff. And it makes sense for the most part, right? Like lithium's atomic number is 3, so it's got 3 protons. The protons and electrons balance. Everything fits together. There's just one problem. In order to get that, you had to round this number to 7. So why did you have to round it? Why wasn't it 7 already? For that matter, why are all the different elements with decimals? When we were balancing equations, we said we couldn't get decimals in chemistry. We said we couldn't have a 1.5 oxygens, right? We said you couldn't do something like this. Making up a number here, but let's just say right here, I said you couldn't do something like have 0.5 O2s because you can't have half an oxygen. And yet I'm apparently okay with having 0.94 of a neutron? As I mentioned to you guys in the various classes when you were in class, chemistry is complicated. We're studying all matter, everything in the universe. And everything in the universe is a lot of things. And that means that sometimes what we are studying is a little more complicated than we can explain right away. You weren't wrong when you broke this down like this. And you weren't wrong to round this number. But you weren't fully right either. There's something else going on, and that something has the name isotope. Now, isotope, like any terminology in any field, means nothing at the moment, but as we get through it, I think you're going to understand. And it has to do with the fact that this is a whole number, and this is not. If you take a look at your notes on page 41, it talks about it a bit. And the key thing is in the very first sentence. The number of neutrons in each atom varies, even between atoms of the same element. This is an idea, a concept that you've probably not been introduced to before, because up until now we try to tell you that everything is exactly the same, and yet it's not. It's not. But how is that possible? How could that possibly be? Well, the example here talks about potassium, which is two rows down from lithium on our table, right? It's element number 19 right down here. And it talks about the fact that potassium can have 20 neutrons, 21 neutrons, or 22 neutrons. it comes in different flavors, different values. And that's strange. Because again, everything up until now has been about absolutes. It is only one way, it is this way and only that way. But it turns out that the universe is a big and complicated place, and just like there are different kinds of people, there are different kinds of cell phones, there are different kinds of pet dogs, there are different kinds of lithium or potassium or carbon. Well, that sounds very distressing now, doesn't it? Whenever we expand things, it always feels like it's going to get a lot more complicated. And it gets somewhat more complicated, but here's the nice thing. It doesn't actually get much more complicated. Take lithium, for example. Lithium has 3 electrons. Okay. If I add another neutron, right? If I come over here and I say, you know what? This lithium put on a little bit of weight. It's got 5 neutrons. Does those 5 neutrons affect the electrons in any way? Right? The neutrons are neutral, so they don't attract the electrons any harder. There's no opposite charges pull, attract. So they don't affect the electrons by attraction, electric attraction. They don't affect the lithium in terms of its shape in any way. It still has 2 inner shell electrons and 1 outer valence electron right there. So despite all of it, there's no appreciable difference in how this lithium behaves. If I were to blindfold you and give you 2 lithium atoms and say, okay, one of these lithium atoms has 5 neutrons and one of them has 4, you would not be able to tell which one is which based on any basic chemistry. Because if I put lithium with, say, fluorine, it'll still behave the same, right? If I bring a fluorine over here, and I'm not drawing out the full fluorine, so I'm just going to put the Lewis structure. If I bring a fluorine over here, the same basic thing will happen. This 1 electron will swing over, come over here, this will become negative, this will become positive. It'll still make lithium fluoride, it will still behave in exactly the same way. There's nothing interesting about its chemistry. It behaves identically. The only thing is it's slightly heavier by 1 atomic mass unit, which is almost nothing. You would not notice it. Like, you literally will not notice it, because these isotopes, these elements that are heavier or lighter than the standard or the default, exist everywhere, including inside of you. Inside of you, right now, this very moment, there will be some number of isotopes making up your hair, your skin, your clothes as well. I mean, that's not part of you unless something has gone terribly wrong. But these isotopes exist everywhere, and yet they effectively have no real effect. At least not for chemistry. They're very important for something else called nuclear power or fission. We don't talk about fission because that's the realm of physicists and atomic bombs and nuclear power plants. For our purposes, though, an isotope doesn't really do anything, broadly. The existence of isotopes was, of course, a surprise, and it threw a lot of things into chaos when they first figured it out, because we kind of assumed that elements would mass or weigh a certain amount. A little known fact that you may not have heard, but the periodic table that we know, where everything is organized by atomic number, it's not how we did it the first time. Originally, we did it by atomic mass, because the masses tend to go up from left to right as well. Tend. Sometimes they don't. Potassium, where is it? There's a famous one. I'm not seeing it here. Yeah, argon is heavier than potassium, for example, and yet argon is earlier than potassium. There are others as well where you've got heavier elements coming first. Doesn't matter much. So when they figured out that the different elements could have different masses, because in this case here, this is like heavy lithium. That's what we call it. It's like lithium that gained weight, so we call it heavy. If it instead was lithium with only 3 neutrons, like so, we'd call it light lithium. You may have heard the term heavy water. Maybe. Heavy water is water that has hydrogen atoms that are heavier than normal, because hydrogen usually has no neutrons. But if you give it a neutron, now it's going to be twice as heavy, because hydrogen has a mass, stick it over here, right? Its atomic number is 1. Its mass is 1.01. Well, if I give it a neutron, the neutron will add an entire atomic mass. So its mass will double to 2, which is not much. That's still half as much as the next heaviest element, which is helium. And helium, as you may remember, floats in air. So even if I make heavy water, it's still half the weight of the next lightest element. Anyway, all of these things were interesting, and the chemists decided that they needed to sort of record some of this information. But, well, that's why these are decimals on the periodic table. It's mostly 7, but enough lithium is slightly lighter than 7, because it looks like this, to make this number just under 7. But how do they do that? Why would they do that? We'll talk about it in a second. First, let's finish going through page 41 here. As you would expect, the different isotopes have different numbers of neutrons. They will have different masses as a result. Remember, the mass is the sum of the protons and the neutrons, right? Because the neutrons are constantly changing, that's why we switched to using the protons to identify elements. The protons are their jersey number on their sports team, right? So it's always the same. Lithium is always player number 3. But sometimes lithium goes on a bit of a diet, so they've got less mass. Other times, not so much. You'll notice here that it talks about how to write these different things. So lithium here that I've written, this would be lithium 3. Let's do it in blue. Lithium 3 would look like this. Oops. Not lithium 3. My bad. There it is. So lithium 6, not 3, lithium 6 means that there are 6 total mass compared to lithium 7, which is the standard. The 3 down below represents the atomic number. So this would be normal, this is lighter than normal, and this one would be heavier than normal. The purpose of putting the atomic number down below is to make sure that the person knows to see how many, right? So like this 3, 6 minus 3 is going to be 3, so there's 3 neutrons. That's why I said lithium 3 at first. And that's kind of it, right? So the examples say potassium 39. That's the other thing here, I should say this. Lithium 6 versus lithium 7, lithium 8. The hyphen is important. It's part of how they know that it's an isotope. So if I asked you guys to write out the symbol for lithium 20, you would go Li, it's lithium, so it's 3, and it's 20. Its mass is 20, which means in this case I have a total neutron count of 17. That's super heavy lithium. But still, each one of those adds 1 atomic mass. So normally lithium is 7. If I add 17, let's see, what would that put me? 7, 4, carry the 1, 34. So that makes it as heavy as chlorine. The other end of the periodic table. Not that big of a difference. And that's kind of it for isotopes in terms of what they are. They're just heavier or lighter versions of existing elements, but they don't have any effect on the chemistry. Not that we do. If you were a nuclear physicist making an atomic bomb for some kind of terrorist organization, please don't do that. Then maybe you'd need to know about isotopes in more detail. That's not the only time. It's not all about doom and gloom. There are some things. You may have heard of carbon dating. Carbon dating allows us to tell if something is old and exactly how old. Because remember, I said that you have isotopes inside of you. You have carbon, oxygen, hydrogen inside your body right now that is heavier or lighter than the carbon-12 that we expect. One of these is called carbon-14 because it has 2 extra neutrons. I hope you can tell that. Carbon-14 is unique because it's created by a variety of complicated processes. We're not going to go there, but when you eat a fresh source of carbon-14, and it enters your body, and your body uses the pieces of your food to make your body, right? That's where the carbon comes from, that makes up who you are. That's why if you don't eat, you lose weight, for example, because you don't have enough material. Well, carbon-14 doesn't occur in dead organic matter. So, a tree, as the tree is growing, it will constantly absorb carbon-14. But the moment it dies, it will fall and it will stop absorbing carbon-14. The net result is that the carbon-14 inside the log is locked in place. It has a fixed amount. But over time, very slowly, like on the span of thousands of years, the 2 extra neutrons of carbon-14 will be kicked out and just leave. And so slowly over time, the carbon-14 will become carbon-12. This means you can tell how old something is by finding out the ratio of carbon-14 to carbon-12, because there is a standard ratio that should exist in nature, but if there's lots of carbon-14, that thing must have been alive and alive recently. If there's very little carbon-14, that means the thing is dead and it must have been dead for a while. There's actually a video in the supplementary links called Things You Don't Know, and it talks about how carbon dating can be used to identify wine, when and where wine was made and what it was made from. Because it turns out wine made from grapes has carbon-14 in it, but wine made from oil from underground does not, because oil from underground is being dead for a long time. Yeah, you could make wine from oil. It would chemically be the same, but people tend to go, I don't want to drink oil. So they made rules saying you're not allowed to make wine from oil, and they test it by using radiocarbon dating, carbon-14 dating. So that's the basics of isotopes, okay? They are elements that have a different number of neutrons. They have more or less, right? So then they could be looking like this, where they've got less here, so this is less than the normal, or they can look like this one, which is more than the normal. The normal, of course, is what you get when you look at the periodic table and you round it to the closest whole number. But what in the world are those decimals? What do they represent? If you flip over the page, we'll talk about what. It says here on page 42, the mass of individual atoms are expressed in atomic mass units. We've already said that before. Or mu. That's what that symbol means, this one here. That's mu. It's a Greek letter. Hey, look, Greek's coming in again. I mentioned it to one of the classes, but older chemists a long time ago, they were kind of language nerds. They knew a lot of languages. The atomic mass unit is defined as 1/12 the mass of carbon atoms. Okay, great. This means that a proton or a neutron has a mass equal to approximately 1 atomic mass unit. Okay, awesome. That's great. We'll work with that. 1 atomic mass unit for a proton or a neutron. In many cases, the amount of each isotope is relative. Can be determined using some machine called a mass spectrometer. Now, we won't talk about how that works. Just believe me, there's a machine. We can turn it on, put stuff in, and we tell you the mass. The relative abundance of an isotope is the percent of each isotope found in an average sample of an element. Okay, so what do I mean by that? If I were to grab my basket of markers here, let's pretend this basket of markers right here, with all my markers in it, is called, I don't know, the markerite element. It's markerite. There it is, markerite. And in it, there are many atoms of that element. I see 5. Okay? Well, let's say that when I reach into my sample and I pull out some markers, these 3 markers all have a mass. And let's say this one here is the standard one, because it's the black marker. It's the standard marker. So we'll say this one is 4. And this one was 5. And this one was 3. So in this particular sample, when I pulled out those 3 markers, I'd be like, oh, okay, so 1/3 of the time I will get a 4, 1/3 of the time I get a 5, and 1/3 of the time I get a 3. So for every 3 markers that I grab, I should get 1 of each possible size. So then if I reach in and I grab another marker, and it conveniently happened to also be a black marker, right? Obviously this one is orange, so I'm going to do a little movie magic here. Boom, black one. And then I look and go, oh, I have 2 blacks and 2 of these. So that means that most of the time I get this one. And if I reach in and pull out another one and I get another black, I go 3 versus just 2 of these guys. So black is the most common. So most of the time I'm going to get this marker. Sometimes I'll grab one of these, but most of the time I get one of these. So that we call relative abundance, meaning abundance means like how much there is, and relative means I'm comparing it. I'm comparing how many times I get one compared to the other. Now, this is why this table and all tables have decimals, because they're not telling you what the normal or the default one has. They're telling you what the average of all of them is. Kind of like, say, you take an average of your final grade. Rather than say, this is what I got on this test and this test and this test and this test, we do a huge average of all the tests. That's what these are. We have here basically the average mass of every one of these elements. Now you'll notice, for example, lithium is really close to 7. So most of the time, lithium, when you pull it out of the ground, is mostly 7. Now, the problem is most of the time is very vague. We need numbers. How often is lithium 7? Well, the way we figure that out is that we take the mass of the particular one, so let's say this one here, so its mass here is 8, and we multiply it by a percentage to figure out its contribution to the total mass. All right, we have an example here. Let's work through the example. That always makes things a little clearer. The example is for magnesium, so sorry lithium, we're going to leave you behind. And let's take a look at what we got. So this particular table says that some chemists have done some experiments. They've collected a whole bunch of samples, and they have found that there are 3 different types of magnesium. Okay, so far so good. So the magnesium options are magnesium 24, 25, and 26. So there's magnesium 24, magnesium 25, and magnesium 26. So the other thing that they did was they said the relative abundance. So basically, when they fished it out of the ground, how many times out of 100 did they grab this guy, and this guy? So when they fished a big sample of magnesium out of the ground, they will pick up about 78.7% of the time, they will get a magnesium 24. So like more than 3/4 of the time, when they reached into the bag, they would pull out magnesium 24. Okay, fair. Magnesium 25, they would reach in and they would pull that out 10.13% of the time. So that's much less, much less, right? Like, we're not even talking 1/4 of the time. And then finally, we've got Mg26 there, and that gets pulled out 11.17% of the time. Okay, so we now have the percentages. The last thing they did was that they took each of these samples and they ran them through that mass spectrometer machine that I mentioned, but not really going to explain too much about. And the mass spectrometer said that, pulled out here so I can do it right, this guy weighed 23.98504. Yeah, we had it down to that many decimals. 24.98584. And finally, 25.98259. Those are some accurate numbers, hopefully. Okay, so what does this mean? Well, again, we want to take an average of all of these to put on our periodic table. Why? That part I don't know, but they did it, so here we go. How do we take an average, right? It's always the same thing. What's your percentage? check your grade. Well, there's the percent, and there's the percent, there's the grade. So what is 78.7% of 23? All of that? Well, we put it together. The exact calculation we're going to use, it tells us right above this table, and it says that the mass contribution, which is what we're looking for here, mass contribution, the way you find it is that you take the mass of the sample, this part here, and you're going to multiply it by the percentage, or the relative abundance, as they call it. So this times this equals that. That's all we got to do. Make sure you turn it into a decimal first. All right, trusty calculator time. We punch it in, and we see that the very first one is going to come up with a number of 18 point, where did I put it? 8765. 8765. And the next one is going to get 2.5310. Why is this so much lower? Well, this is a bigger number, but I'm only taking 10% of it, right? So you got like 10% on that test. So you didn't put much towards your final grade. Whereas you got 78% on that test, so that bumped a lot, your grade up really a lot. This last one here is going to get just a little bit, so it ends up with 2.9. 2.9022. Now, these are the averages of every one of the elements that we can pull out of the ground. These are the averages of the tests, right? So you did 3 tests in this unit, these 3 tests, boom, boom, boom. You got these percentages, boom, boom, boom. And these are the total marks you could have gotten. These are the marks you actually got. Ooh, these last 2 didn't go well. Now, to find out your final grade, you just add them up. And when you add all these up, you get 24.3097. If you take a look at your periodic table, you will see that magnesium is 24.31. The 9 rounds up to 1. So the reason why the magnesium is 24 but slightly heavier is because if you look, 24 is the most common, but there are 2 that are heavier. These 2 guys are slightly heavier, but there's not much of it. So the average is pushed a little bit higher. Again, using the grade analogy, you basically did great on this one test, but you didn't do great on the next 2 tests, which means that your grade didn't go up much from the test you did well at. And that's kind of it. Calculating the relative abundance and the relative atomic mass is really just you just do it. If you guys take a look on page 43, there are some example questions of this. Similar, there are some example questions of more of this stuff on page 44, 45, and that's it. 44 and 45. So calculating isotope abundance is not hard, but it is a weighted average, which is exactly what your grades are. So in theory, you guys are very familiar with them, but I've generally found that most people do struggle a bit with weighted averages. So the key thing is, a weighted average is that you're just taking the mass of the thing, right? So this is the value, and the percentage. So the total marks and the marks you actually got. That's all. Percentage, marks, there's the marks you actually got contributing to your final grade. It's the same thing. We're basically grading the elements, and for the most part, it works out fine. Now, generally, people will ask me, hey, what's up with oxygen? Why is oxygen exactly 16? Is there no isotopes for that? No, there are. There are isotopes, but it turns out that the exact math balances out to be perfectly 16, so surprise. Sometimes math is weird. Similar, people will ask, what about the elements that don't have decimals? What does that mean? That means we haven't been able to find any isotopes yet. If they're in brackets, especially, that means we haven't actually been able to weigh them yet, or mass them, technically. Every time we've tried, they've either decomposed, blown something up, or some other weird thing. So a lot of the ones don't exist, or at least we don't know enough yet to be able to say anything. Okay, isotopes. They're pretty weird. When it comes to the math, it's literally just do this, add them up. So like doing it isn't hard. It's usually just that people have a hard time wrapping their brain around it. Just remember, it's the reason why atoms, elements on the periodic table have decimal masses, because it turns out that elements come in different weights. Some of them are heavy, some of them are light. And that's kind of it. This particular thing is going to be in isolation. If you guys continue into forensic anthropology or archaeology, or you continue into maybe forensics for crimes, or if you continue into nuclear physics, then or medicinal physics, then this stuff will become very important. But for the rest of us, it's cool to know that there's more than one type, and it can make some interesting questions like what happens if all of the hydrogen in your body were replaced with heavy hydrogen, hydrogen that is twice as heavy? Would you notice? Would you feel anything, or would it not matter? Like, not just one or two, like all of them. But these are pretty theoretical questions. So try these, see what you guys can do, ask questions if you're a little stuck. But for the most part, there's not much to this. It really just comes down to understanding this is where we get the mass number that is on the periodic table, and we're showing you how we get it. Previously, we just said, this is what it is. Now you know why it's this, and now you see how to get it. And that's the key. So I will leave it there, and this is basically the last lesson. All right, technically there is one more thing. But because I want to make sure to keep this isotope video separate, I'm going to actually make that last video literally separate, but it's going to be really quick. Like, painfully quick. But we'll do that separate. So, see you guys next time, which will be in like 5 seconds.